Okay, let's try the derivation of kinetic energy. That's what we need to know. So EK, the kinetic energy, equals half mv squared. What I need you to do is I need you to look at this and I need you to think v squared to start with, because that's going to be our first step in our thinking. The reason I wanted you to think about v squared was so that you could remember to use the suvat, which is v squared equals u squared plus 2as. What I need you to do is I need you to say as part of your answer that you're going to take u as 0. It's going to be something that's starting at rest, and I want you to get s as the main part of this equation. I want you to rearrange it so s equals v squared divided by 2a. This is our first point of call before we use more equations in order to derive kinetic energy. So we've got our rearranged suvat equation, s equals v squared over 2a. And the next thing we need to consider is what is the kinetic energy. It's energy, it's in joules, and it's equivalent to the amount of work that can be done. So we say work done equals force times distance moved in the direction of the force. We also know that F equals ma, and with these two we can combine them and we get W equals max, which is an odd looking one. W equals max. So there we go. S equals v squared over 2a, our rearranged suvat. W equals max, the mass times acceleration times the displacement. Now, what's important here is s and x are actually exactly the same things. So, we can just substitute one into the other. We're going to say that W equals m times a times v squared divided by 2a. Of course, we can just get rid of those a's, they cancel, and as you can see we're left with half mv squared. So as long as we say that all that work done becomes that kinetic energy, we have our final answer, don't we? We have W, which is kinetic energy, and then we have 1 over, that's our half, times by m, times by v squared. So write it up neat and it all looks great. That's the answer to our derivation.